Okie dokie dokie, welcome back. We are going to do the eyes. Me alive. Me alive. Yeah. Anyway, we're gonna make our eyes. Done all this. Time for this. Our eyes object. And we're going to get started by doing what? Creating a class and saying eyes. I'll just call it eyes. And what do we need to construct a set of eyes? A blueprint. Well, that was predictable. Anyways, we will name it eyes, name the files, same as the object. Yep. And it will create this header and CPP file for my eyes object. Of course, we can do the standard mantra of renaming who created it from my computer's name to my name, my nickname anyway. And of course, a class has a private area and a public area. So far, so good. And we don't want this. Eclipse drops in there for us. And of course, what are we going to make the eyes out of? What are we going to include? A sonic sensor and an angular stepper motor. Include sonic sensor. Include angular stepper motor. And of course, I don't see a reason why they should be public. Because we're going to, the eyes for the robot are going to be one device. So there's no reason to micromanage any of its subcomponents at this point. So making them private would be appropriate. Sonic sensor. From the blueprint of sonic sensor, we will make a sonic sensor. Yeah, we'll call it sonic sensor. Sounds appropriate to me. And of course, from the angular stepper motor blueprint, we are going to make we can call it motor, stepper motor, angular motor. Let's just call it servo motor. Yeah, that'll work. Just give it a generic name, Of course, since these are private, I'm going to remind myself that they're always private members by putting an M underscore in front of each of the names. In standardized tradition. I like that. I like this. I've looked at different alternatives that people do. I like this one the best. Yeah. And now, what do we want from this? Now, remember, we're increasing intelligence and we're delegating it as a higher command now. We're not worried about the individual parts. We're worried about this as a unit. And as a unit, this is what I think I want. This is what I think would be cool or appropriate. As a unit, when the eyes are looking forward, I want to call that look forward direction. I want to call it 0. And if I want to look to the right, like say 10 degrees from forward, I want to say plus 10 degrees. And if I want to look to the left, 10 degrees from 0 the other way, I can say minus 10 degrees. And I think that'd be cool, rather than this 0, which is actually where the motor's at, and 180, and this being 90. Let the details work themselves out. What I want, In other words, mini tank, the boss, or the next layer up, I think would be cool, is just to say, hey, eyes look forward, eyes look right, eyes look left. Now, I'd like to be able to set that angle, of course, but we need to know how far you can look to the right max, how far you can look to the left max. So that would be 0 would be forward, straight ahead. To the far left would be minus 90, and to the far right would be plus 90. And of course, we can do a little bit of math to figure out what signal to send to the motor separately. I think that's what I want. So we'll set some properties. We'll say, okay, this is our properties. This is what we want. Enumeration. That sounds good to me. With the context of enumerators or values whose has name assignments. And we say looking ahead. We'll just call it look ahead. Look ahead equals 0. Look far right equals all right. I guess it would be 90. And look far left equals minus 90. Yeah. And then maximum right equals 90. And maximum left equals negative 90. Now, why did I do it twice? Why did I define 90 and minus 90 twice? Well, I just wanted two different names that, in case I wanted to use look far right, or if I want to use maximum right or maximum left, just for fun. That way I could choose which one. Like say if I'm doing a calculation, I need to know what the maximum allowed is. But if I just want to look to the far right, let's say the mini tank wants to, hey, the eyes go look far right. I can use this word. And it means the same thing, but, it makes my code a little more readable, I think. All right, we'll find out. I'm just taking a guess at this point. I haven't programmed that far. I don't know if anybody's aware of this, but I am programming this, the majority of this from the hip. Just it's coming out of my head and plopping on the keyboard here. So it's not like I have this pre-made, preset, plan. It's just, this is how you program. You think, you do, and you make mistakes, or you come up with things and you say, oh, I need to, Ugh. Anyhow. Okay. Now, we have a sonic sensor and a servo motor, and our sonic sensor, according to this wonderfully cryptic, unintelligible that came with this unit. My servo motor pin is going to be, we figured out, pin 9. Our sonic sensor, echo, and trigger pins are going to be 4 and 5. And I think that's all we need, because we need a trigger pin, echo pin for the sonic sensor, and a PWM pin for the angular stepper motor. So the eyes, in this layer, I'm going to assign those pins instead of making the mini tank do it, because this eyes is going to be proprietary to the mini tank, and this only one project for now. So that's at the proprietary layer is where you at the start of the proprietary layers is where you start to define pins and specific things to your specific project. Anyway, let's go do that too. But those are private things, so we can make a private enumerators out of those, and we will name those pin numbers. So we will say, let's say, servo motor pin is equal to, what was it, pin 9. And our, of course it only had one, Arduino connectivity, only one pin. And our sonic sensor, the sonic sensor trigger pin, of course, let's make this a little prettier. I think was pin 5. Yeah, that's what it was, I think. Let me make sure. The trigger pin, pin 5, and the echo pin, pin 4. And then, of course, sonic sensor echo pin is equal to pin 4. Yeah, that looks pretty good. Yeah, a little better. There you go. And of course, to assign those pins, we're going to do it during the construction process. Hey, when you're building this eyes, one of these eyes, or a set of eyes from my blueprint idea here, I want you to do something. I want you to set those pin numbers in those subcomponents. Blueprint. Now, we're not going to ask for anything in our construction process because everything we need to know is actually here already. But we do need a constructor. And how you make a constructor for a class? The name of the class. In our case, it's usually and quite often Blueprint. Alright, now we need, of course, a way to instantiate, initialize, start up, crank, start the engine. This is what you do when you apply power before anything else, kind of thing, when you're getting ready to do your thing. We need a routine to tell those sonic sensors and motors and subcomponents, because they have a begin routine to get them cranked up and going. We need a higher level begin routine, and we're just going to call it the same name, so that the mini tank itself can call, hey, eyes begin, and then eyes. This routine will inevitably, how do you do this routine? Well, you go and you say sonic sensor begin, motor begin, this begin, that begin, and it kind of follows this flow, like I mentioned earlier when I was doing the tank tracks. Same kind of flow, same thing. We're just delegating downwards in a spidery fashion as we go, and that's how it will get these things done. And we also need, I don't think we only, I think, yeah, I think we only need one other thing publicly. In other words, that the next object up manipulating these eyes needs, and that's to get the collision distance. How far is it to an object when you're looking. But in this case, like I said, I want to be able to get the collision distance at whatever angle I want, and that angle is going to be 0 going forward and all the way to plus 90 and minus 90. So I want to get collision distance, kind of like the same thing as the sonic sensor does, but I want to be able to set that angle. So I'm going to just call it the same thing and just make it and require that an angle be specified. And then, of course, what are we going to get back? We'll just make it the same as what the sonic sensor gets back. We can make it 0 to 55 centimeters because that's what it's going to give me. So that's an 8-bit value. So poop me out an 8-bit value from my little, my function critter, and say get collision distance. And then we can't have a UI and 8T, can we? Angle. Okay, now, since angle is going to be 0 to plus 90, I suppose it can be 0 to plus 90. It can't be unsigned, though. Or 0 to minus 90. We can't have it unsigned, so let's get rid of the U. Now, is an 8-bit value going to be big enough? Well, an 8-bit value that's signed, which means it'll go from 0 to negative something and 0 to positive something, assigned 8-bit value only goes from 0 to minus 127 and plus 127. So we are covered there. Because if you take an unsigned that's 0 to 255, you split it in half because you're using the same data space, the same number of bits, that's what you end up with. That's how it works. Anyway, enough rambling. I think that's all we need there. Is there anything else? Not really. I think we're good. So let's implement all these methods and teach the compiler how to do the things that we're asking for, how to do these abilities. How do I do them? Well, let's stick that over in the CPP file, and of course, Eclipse makes us these things, so we don't have to type them in. We refer to eyes, the blueprint class, and then the blueprint function. Here's the context of how you do this. Eyes, blueprint this, blueprint that. Here's how you do that. And I am cooking a bit of something, and my timer has gone off. And I will pause and come back. Okay, let me set my timer again so I can go stir my pot of food. I'm cooking on the stove. Anyway, alright. So during the construction process, we're not going to require any information, but we need a, by the way, set those pins to those values for those subcomponents. And we don't need to perform any tasks, so we'll leave that blank. And we'll say, hey, by the way, our M underscore component servo motor, we need to set that to something, comma, M underscore sonic sensor, we need to set that to something. And what we are going to set that to is the let's go look at this real quick. Okay, we have a servo motor, angular motor. We call it a servo motor, but it's actually an angular motor. If we hold our mouse over this, you see how it just says class blueprint. It shows what we actually wrote earlier. Okay, and I never covered this, and it's appropriate at some point to probably mention this, so I'll mention it here. Hey, why not? It's not really required, but if we highlight over this, we can't readily easily see what information we need. We have to go in here, we have to find the blueprint routine. You see how it's right here? We have to find the blueprint routine. But if we were to do this and put it as a comment, and say use like this, right? And then make this a comment. Oh, I don't know why this. There we go. Start a comment and then end our comment, or we can just simply, if it's a one-liner, we can just do this. One-line comments looks like that. And we'll just make it a one-line comment. And we type use, and we put this right here, and then we do this. Then what happens is the editor, this Eclipse, software editor, when we go over here to another area of our code and we go to look at our blueprint, what happens is we highlight over it. You see that? It says use, blueprint, and control pin number. Okay, so we did that. If we took the time to do this to all of our subcomponents and our subcomponents. In fact, why don't we do that? Why don't we just say tracks, and we say here we say use. Okay, and then we say eyes, and we say use, and we do that for every one of our header files. Bidirectional motor. And then of course this one requires data use. Of course, direction pin number. You know what? We can leave the data type. Yeah, that way we know what data type, what size data it needs. I guess we could leave that in there too. I'll go back to the other one and fix it. I think that was it was the angular stepper motor. Yeah, let's just leave it like this. That way it's the same for all of them. There we go. I don't always do that. I don't generally do that, but it's not bad practice since we're here and we're talking about it. We did this one. Did we do the sonic sensor? No, we didn't. Use. Copy. There we go. And yeah, that's all of them. Anyway, so I closed one too many files. There we go. Now we go over here and we say blueprint. Our servo motor requires a control pin number. That's the first line that pops up. So, and that's the order in which we have to define it too, or put it in here. So we can say, what did we call that? Oh, servo motor pin. What we called it. Servo motor pin. There we go. So our sonic sensor requires a servo motor pin. No, it don't. Our servo motor requires a servo motor pin. Yeah, I need to go drink another beer. And then our sonic sensor. And if we hold this over this, we see that we need a trigger pin, comma, and echo pin number. And a trigger pin number. Trigger pin, comma, echo pin. That's the order. So we say sonic sensor. Trigger pin, comma, sonic sensor, echo pin. Now what that's going to do is say, by the way, blueprint, during the construction, by the way, I want the servo motor item, the specific item I created from your blueprint, to ingest the pin number so that it gets set during construction process, and same thing with sonic sensor and its pin numbers. Now the begin routine, I want to take my objects, my subcomponents, and I want them to crank up and run during the begin routine of this thing that cranks up and runs. Dot begin. There we go. And the of course the sonic sensor needs to have its routine run so it can initialize whatever pins and gobbly-gops that are inside it of unknown mystery at this point. There we go. And then get collision distance. Now I have 11 seconds and I have to stir my food, so I will pause and come back again. Okay, I stirred my food. Now we have an angle, and remember it's an INT 8-bit, and it goes 0 to plus or minus 127, so we need to deal with clipping its wings, is what I call it, because we only want it to be able to go from 0 to plus or minus 90, because the angular stepper motor will only go 0 to 180. So to clip its wings, if a frog had wings, he would not bump his patootie when he hopped. Servo motor or how about servo look ahead offset. equals 90. There we go. Yeah, that looks good. Angle is less than our, let's look at this a little differently. Why don't we say, why don't we make another enumerator and call it yeah, why don't we make another enumerator? In fact, we'll make a local one just for fun. Enumerator. And we'll call this out of bounds. We'll do this, we'll do a bounds checking. We'll do a little different this time than we did last time. Instead of if it's less than this and if it's less than that, and you use our maximum on our thing. Let's do a little different way this time, just for fun. Out of bounds equals 90. Okay? So if angle is less than negative out of bounds, and there's a reason for this, just bear with me, I'll show the reason for this. Then obviously angle is equal to negative out of bounds. Out of bounds doesn't seem appropriate there though, does it? Angle limit. Angle limiter. How about that? We'll call it angle limiter. And of course, I'll go ahead and shorten this up too. It's actually a little easier to read with it shortened up. And then of course, if angle is greater than our positive value of angle limiter, then angle A is going to be equal to the angle limiter, the positive value. So basically I'm saying if it's less than negative, of course this number is 90. If it's less than negative 90, then make it negative 90. If it's greater than positive 90, make it 90. And this is a different way of doing it. I know we, where did we do that before? We did it in our bidirectional motor. Of course, we added a little more logic to it, but we said if speed is less than our negative 255 here, because we're using it in 16, if speed is less than our lower bounds here, basically, set it to the lower bounds, and if speed is greater than the upper bounds here, we set it here too. We did the same thing here, but I want to show a little different way of doing exactly that logic for a different reason. Basically, you define a limiter and you just set a value to it. Of course, it's usually defaults a positive number. Of course, in this case, it's an angle limiter, so we call it angle limiter. And we do a bounds check on it. Basically, we say, hey, if it's lower than the negative of the limiter, then we set it to the negative limiter, and if it's higher than the positive limiter. Why would we do this versus just simply saying, and add this enumeration in here, rather than just simply saying, the same thing can be defined, maximum right and maximum left. You see we have here, which would actually get us the same thing, but it would look like this, okay? And then maximum right. And I'll show why someone would want to do this a different way, just for example here. And of course we have the word right. And this accomplishes the same thing, but it doesn't. It actually doesn't. And here's why. If angle is less than negative 90, and up here we have an angle is less than 90, and we put this negative on it, which is negative 90. This is equivalent to this when it runs as it sits. But, and here's why, sometimes you would want to do things or code things in the how to, here's how to do this function a little differently from this, because what were to happen if I decided that my eyes, I said, okay, go positive 90, and which means maximum right would be this way. Of course, camera's kind of screwed. If I say positive 90 is this way and negative 90 is this way, and then I actually run the motor or something happens, and then I say, whoa, wait a minute, positive 90 is actually this way. So it's I need to reverse that logic, or I need to, in other words, maybe I find out later that this should be a negative 90 and this should be a positive 90. And it should be the other way around. Well, if I do that, then that totally, basically destroys this if statement. It destroys this, because if I save this now it's going to say if angle is less than 90, which means it could be 0, it could be 15 degrees, it could be 20 degrees, set it to negative 90. So I'll never be able to go anything but positive or negative 90 now. I won't be able to go 5 degrees. I won't be able to go 0 degrees. So it destroys this logic completely. Okay, so sometimes you want to do a bounds check or a range check on something. Sometimes you may not want to use something like this if there's a possibility that you'll end up altering it later. So I wanted to show that as like a secondary way of doing a bounds check. Where it's not so dependent upon the settings in the main header file, just in case, those end up getting altered. Now, of course, in this case, they're not, I don't think. I guess we'll find out the hard way later. Right and left. In other words, we could actually swap right and left just by simply swapping those values. But if we did that, like I said, this logic here, where we're relying on that data, because we have to do a less than for a negative number and a greater than for a positive number, it kind of destroys this. But in this method here, if we use it like this, our limit is going to be simply 90, whichever direction that's going to be. And if I say our angle is less than a negative of that limit, then set it to the negative. That's going to get us, no matter what we set this to up here, it's not going to destroy this logic. So, Now, because we have some logic going on here, we can actually take and make a local command out of this. So why don't we do that instead of bringing this out in 3 lines of code? Why don't we just make it a little more clear what we're doing, and why don't we say ensure within bounds angle Of course, we can make that a private function, and we can make it void because we don't really need anything back. And then we can use we can use the address of, which means edit live. In other words, edit whatever's being whatever's being supplied to it live, rather than give something back and take something in and copy it. And of course, this is going to be an int, a data type, and then of course we can send that to our private area. Don't look, it's private. Ooh, it's private. And make a private function out of that. And of course, how do you do that? Hey compiler, how do you implement methods so that we can tell the compiler how do we implement that? Simply like this. Like so. And then of course ensure within bounds, and of course we want to inline that because we don't actually do the logic here. We don't want it to jump off up over here and say what you're doing and all this garbage. We want it inline. So inline So there you go. Ensure within bounds angle. Now when it passes this line of code, it's going to say, hey, because we sent the address of, I think I might have covered some of this before, but when you put an ampersand, it says instead of taking angle, making a copy of it and using it over here, we want to say edit literally this memory address of this, so that if I change the value, like here I change the value of angle, the memory address of angle, which is actually this copy of the variable. So as it goes from here to here to here, it will actually alter our data. And that's pretty cool. It's a nice little feature of C++. You can, and the reason why that feature exists is because what if I had a function and I needed to supply it 3 pieces of data, let's say, and I needed back 3 pieces of data. The way a function is designed in C++, it'll only poop back 1 piece of data. So the way you get 3 pieces of data in and out is to use the addresses of whatever those pieces of data is, comma, comma, comma. And then you can get those multiple pieces of data to be altered live, and then that would be a result rather than having to return something. So that's how those kind of functions work. And of course, now that we've done a bounds check, we can't send angle, because of a positive negative number, to our servo angular stepper motor, or basically our servo motor. So we need to translate that, and so we can just say uint8t, which is going to be the 0 to 180. The servo motor takes 0 to 180, which it's always positive value, and we can say motor angle, the angle we're going to send to the motor. And then we can say equals to our servo look ahead offset, which we have set here. We put in a servo look ahead offset, and then we say, hey, servo look ahead offset plus the angle we want. And what that will do is take, if it's 0, obviously, if the angle we want is 0, like I said, we want to say if it's 0, look forward. If it's positive 90, look this way, negative 90, look this way. So if it's 0, it's going to say motor angle is going to be the 90 plus 0, which is 90, which actually on this thing it is 90 looking forward. And of course, we're going to add or subtract to that to get the motor to go where we want to. And of course, the next thing to do is send it to the motor, m servo motor dot set angle, and of course that's the raw angle of the motor angle. And then the next thing we need to do, the last thing we need to do before the exit, and we'll get to the middle part, is we need to send back an 8-bit value, unsigned 8-bit value of centimeters of get collision distance. We can just literally take whatever the sonic sensor is giving us and give it as our result. Return our m underscore sonic sensor dot get collision distance. So we're going to say, hey, run up, get us a collision distance. However you're going to do that. We don't want to know at this point because we already programmed it and we're done with that area. We just want you to do it and return that. Whatever you spit back and poop back out at us, we're going to poop back out as our result to this whole higher level or function that actually does it at a certain angle versus just where you're sitting. Yeah. Now, if you leave it like this, it's going to tell the servo motor or angular stepper motor, whatever you want to call it, it's going to tell our motor to start moving towards that angle, and then immediately it's going to say, hey, go get my collision distance. Problem is, the motor takes time to get over there, and this thing's running a million lines of code a second. So yeah, we may end up with a problem. It may start to move, and then we check it, and we may never actually be over there before we check it. So we need to wait for the motor to actually achieve its position. And since we programmed it the way we did, we can say, there's one way, one way to wait for something is with a delay. We're not going to use a delay. We can do it with a loop, and we can do it with a do something while some condition is true. We can do everything in this context while some condition is true. That's one way to just simply sit in loop and wait and keep checking. Hey, have you gotten there? Have you gotten there? Have you gotten there? And of course, what are we checking? The m_servo. Are you in position yet or not? But there's another way to do a loop, and let's just say while some condition is met, execute whatever code in this context, which is the same. Basically, both of them are the same things, except this one. The difference is this one will do the context no matter what, and then check. While this one will only do the context only if this is set beforehand, or this is true beforehand, which means it won't bother to do anything in here if this is not true. So we're going to use this one, and we're going to say if the servo motor has arrived, in other words, if it has arrived, but we don't want to know if it has gotten there. We want it to know if it has not reached there yet. In other words, we set the angle. Have you not reached your position yet? No, we have not. I want you to do nothing, just nothing, and then check again, and keep checking until that motor has arrived. And don't go past this line of code until that motor has arrived. Just keep looping into nothing. There we go. Now, because we're not doing anything, we actually don't even need those brackets, so we can just say this. While the servo motor has not arrived, but I like to sometimes, most of the time I'll do nothing. I like to at least show that the context is empty. Or you could put a comment in there, like this. Some people will, I've seen some people do this. Keep waiting. Or something like this, or they'll describe why they're sitting there doing nothing in a comment. But yeah, that works. We'll do it like that. We'll just that's plain and simple. While the motor's not arrived, just do nothing. Just keep waiting. And then, of course, after you waited, give me back. After I know the motor has gotten there, check the collision distance and give it back to me live. That looks pretty good. Yeah. So basically, get the collision distance at a specific angle versus just where you're sitting. Ensure my angle I'm requesting is within bounds. Determine the motor angle from the main angle I want. Set the motor angle, the motor to the motor angle. Wait for the motor to get there, and then check what's in front of the eyes.